In this video, we're going to be talking about how to evaluate the limits at infinity of rational expressions. So if you look at this particular limit as x approaches infinity of 3x plus 1 divided by x minus 2, if you take a really large number, multiply it by 3, and add 1, you get a really large number. If you take a really large number and subtract 2 from it, you get a really large number. So this is approaching infinity over infinity, which is what's called an indeterminate form. We don't know anything at this point about how to evaluate this. So one thing that you can do is a trick which will allow you to actually evaluate this limit using some of the rules that we've had so far. So I'm just going to rewrite my limit for a second here. And as long as I multiply the numerator and the denominator by the same thing, that's perfectly legal. So I'm going to choose the degree of the denominator, and I'm going to multiply this by 1 over x divided by 1 over x. So 1 over x to the degree of the denominator. So that gives me the limit as x approaches infinity. 3x times 1 over x is 3. 1 times 1 over x is 1 over x. And on the bottom I would have 1 minus 2 over x. So if you look at this now, you've got constants and you've got a number divided by x to a power. So I could think of this as the limit as x approaches infinity of 3 plus the limit as x approaches infinity of 1 over x divided by the limit as x approaches infinity of 1 minus the limit as x approaches infinity of 2 over x. And this is perfectly fine as long as you don't have a denominator that would be equal to 0, which in this case you don't. So this is 3 plus 0 divided by 1 minus 0, or 3 over 1, or 3. And that is the limit. Now, of course, you could evaluate this by plugging in values that are really large, maybe increasing powers of 10 or something like that, and you would see that it would approach 3. So let's look at another one. In this case, I'm going to multiply by 1 over the denominator's degree. So I'm going to multiply the top by 1 over x squared and the bottom by 1 over x squared. So I get the limit as x approaches infinity of 2 over x minus 4 over x squared divided by 1 plus 7 over x squared. So this is the limit as x approaches infinity of 2 over x minus the limit as x approaches infinity of 4 over x squared divided by the limit as x approaches infinity of 1 plus the limit as x approaches infinity of 7 over x squared. So again, I have a constant and all of the other limits are that c over x to the r. So I get 0 minus 0 over 1 plus 0, which is 0 over 1, and that's 0. So my answer here is 0. And one more. Again, the degree of my denominator here is 1, so I'm going to multiply this one by 1 over x divided by 1 over x. So that will give me the limit as x approaches infinity of 4x minus 1 plus 1 over x divided by 5 plus 3 over x. And this actually breaks down into 5 separate limits that have the limit as x approaches infinity of 4x minus the limit as x approaches infinity of 1 plus the limit as x approaches infinity of 1 over x divided by the limit as x approaches infinity of 5 plus the limit as x approaches infinity of 3 over x. So this one goes to 0, this one goes to 0, all of the other ones are going to evaluate to something else. If you take infinity and you multiply it by 4, it's like you've got an infinitely large number minus 1 plus 0 over 5 plus 0. Now I put that infinity in quotes because you can't be equal to infinity, but if you take an infinitely large number, you subtract 1 from it and you divide it by 5, it's still infinitely large. So this limit actually evaluates to infinity. So that would be the answer. It's approaching infinity. It's increasing without bound. So hopefully you'll see a pattern here. In this particular example, part A, the first degree, both the numerator and the denominator will raise to the first degree. They have the same degree. On this one, where the answer ended up being 0, the denominator had a higher degree of x squared. And on this one, the numerator had a higher degree of x squared, and the denominator was just 1, or x to the first power. So, and this answer went to infinity. So one way that you can think of this is it's kind of like a race between the numerator and the denominator. Which part is growing faster? And when you talk about growing asymptotically like that, you only are really concerned with the highest degree term. So this is kind of a shortcut that you can use so you don't have to go through this process every single time. This is the guidelines for finding the limits at plus or minus infinity of rational functions. If the degree of the numerator is less than the degree of the denominator, then the limit of the rational function is 0. If the degree of the numerator is equal to the degree of the denominator, then the limit of the rational function is the ratio of leading coefficients. And if the degree of the numerator is greater than the degree of the denominator, then the limit of the rational function does not exist. So what that means is it's going to go towards plus or minus infinity depending on signs. So let's take a look at this one. Up here, if you want to call them m and n, my m would be 2, my n would be 4. So in this case, the denominator wins. So this one goes to 0. Here we have an m of 3, and we have an n of 3 because we've got a cube and a cube. So this one is going to be the ratio of leading coefficients. So that'll be 3 divided by -5, or -3/5. So those are my answers. And in this case, my m would be 2 and my n would be 1, so the numerator would win. And this is going to go to plus or minus infinity, and you just want to check. I've got a large positive number that's being squared and divided by a large positive number, so that is going to be positive infinity. So that would be my answer there.